All right. Hey guys. Um, I am just starting this a little bit late. I've worked all weekend on this report. It took me forever. I think it's been like 6 hours uh, yesterday and then several more today. Um, just getting around to putting this together. So I had a lot of fun doing this one. The whole project was a lot of fun for me. I think number one was actually my favorite because, uh, for one thing, I'm a physics major, and physics is my favorite of all the sciences. So this one was a real blast for me. Um, the thing that I found to be most interesting out of that Scale of the Universe webpage that we looked at was the nebulae, particularly the pillars of creation. That was the most interesting to me. Getting to start at the size of human and then moving out and seeing from there how just massive the pillars of creation really are, um, is just, it's absolutely mind blowing. It's incomprehensible, really. So let's see. So I also really enjoyed that speaker that we saw on YouTube. He was really interesting. I plan on actually watching more of his videos because I really didn't want the video to end. I was really into it. So with this one, what we did was we were seeing it standing still relative to the universe, how fast we actually are going. And so we got to calculate based on the speed in miles per hour how fast we were truly going. And all my calculations are in here. I remember seeing that we had to show our calculations. So here's my chart where I called it the speed of the universe. We've got Earth's rotation at 0% of this chart. Is that just one? It looks like more. No, it's just one. Earth's orbit is at 0% as well. The solar system orbit was 9%. The Milky Way orbit was 9%. I redid this graph actually several times because it showed the Andromeda galaxy speed at 0%, which didn't seem correct to me. I guess in my mind, it needed to be all together, like, smaller, get bigger, 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 bigger. But I mean, it makes sense because the solar system orbit is going faster than the Andromeda galaxy speed. So I imagine that it's right. And then the local group at 32%. Actually, now that I'm looking at it, I think I screwed up and I added my total into here. I will correct that, Miss Benzie, before I submit it to you. So here's my bar graph showing the same information, that the Earth rotation is going at 0. Earth orbit, a little bit faster. Solar system orbit, even faster. Andromeda speed, not that fast. And then the Milky Way orbit, and then the local group being going much faster than everything else in comparison. So my report was that seeing the scale differences in size between us and everything else in the universe is mind-blowing. I was particularly blown away by the size of humans in relation to the size of celestial bodies. The incredible difference in scale between us and the pillars of creation is almost too mammoth to comprehend. While standing still at the equator, you would technically be traveling at 7,256,537 miles per hour. And then just because I'm a show off, I put it in scientific notation as well. Measurement is all relative. For example, when Nassim Haramein discusses the speed at moving your hand, you can measure that speed at 0.5 miles per hour relative to the idea that standing still is 0 miles per hour. Or you can measure that speed in relation to the universe, in which case I think would mean it would be moving at 7,256,537.5 miles per hour. It's just assume you're just adding that half of a mile per hour, but I might be wrong about that. Hopefully not. Large and small numbers are recorded in scientific notation for ease of understanding rather than having to count the zeros in that big long number that I literally just held down zeros just for my example. And then I had to actually figure out that that number was 100 billion or 10 to the 11th power. So for number 2, I really liked this one also. I think discrediting things on the internet or things in the news, things like that, that say that it's true, and people just believe it and they don't fact check, which is incredible to me. But this one was fun to see. So we showed that the presidents in this bar graph, they showed us that it looks like a large difference between the unemployment rate percentage in Clinton years and in Bush years. Looks like Clinton was much more horrible than Bush. But when we zeroed out that y-axis here, in actuality, there really wasn't that big of a difference, which you can, if you just look at the numbers, you can see that it's not that big of a difference. And then again with the bowlers, we showed Diana, Hildy, and Emily, that they look like there's a huge difference between all them, but really it's not that big of a difference. Emily's not all that much better than Diana, only making 7 more, which I don't really know much about bowling scores, so I assume that's just 1 more strike or something. I don't know. Okay, so on this one, we looked at this pie chart. So the pie chart blew me away even more because a bar graph, I see how they can kind of fudge it and they can take that y-axis and instead of putting it at 0 where it should be to show accurate data, they leave it, at 5 to show inaccurate data. Really, it's almost like you've just zoomed in on that bar graph and made it look like it's very far apart when really it's just right here. But the pie chart is just a straight up lie, which to me, I don't even understand how they can get away with that. But anyways, so they're showing that it looks like the city did half of funding, Unknown did this large section of funding, Maloof's did, looks like, I don't know what, a quarter of the funding, and AEG did, it looks like a little less than that. When really, when we recreated it here, the city did a lot. Unknown didn't do a whole lot. AEG did 12%, and then Maloof's did 21%, which is about a quarter. So they had at least that part of it right. And then over here we looked at this little chart, which now that I'm looking at it, it looks like this is almost ovalish. But oh, you know what? I wonder if it's because when I was formatting down below, if I pulled when I pulled my columns to widen them, if I made it look more ovally because of that. I wonder if that drags it. So on here, we looked at the percent of sales. These are the actual percent of sales, and we created our own pie chart and then compared that to this one that we were given, in which case Cartera showed what is essentially about a 16% size in their little piece of the pie here, when really they only had 4%. So I don't know if the motive behind this would be to look like they've accomplished more than they have. I don't know who they'd be presenting this to, but it's definitely interesting. So my report was that it is shocking how something that is meant to illustrate scientific data can be and is manipulated to show false outcomes. Some people may want to practice this deception in order to sway opinion in a desired direction, like with the political stuff. Others might be covering up undesirable truth, like maybe the Cartera not selling as much. These seem to be motives in some of the examples that were used in this exercise. I never realized that a bar graph could be manipulated to show a different perception of data, By simply changing the starting values in the y-axis of a graph, results can look extremely skewed. Doing this can exaggerate the difference in data. Measuring the Cartera graph was fun and interesting. Measuring the pie charts gave me insight into how false information is reported. It's amazing that even news stations report incorrect data with pie chart illustrations that are completely inaccurate. In the Cartera graph, the company illustrated their percentage of sales with a section that has an area of roughly 16% of the whole, covering up the fact that their achievements were only 1/4 of that amount. Had they really wanted to be deceptive, they would have omitted the data callouts in the chart so that the observer wouldn't even realize that their sales were only 4%. Which is something that occurred to me when initially looking at this. Was when I very first saw it, I kind of knew where we were going, aside from the title of the lesson, because I could see right on there that it says 4.5%. Right next to these that say 23, 24%. And it, immediately struck me as like, well, that's not accurate. An accurate illustration, I mean. So it's possible the data can be inaccurately depicted this way unintentionally. I wanted to give some of these folks the benefit of the doubt. For example, prior to this assignment, when making a bar graph in Excel, I personally did not realize that for accuracy of reporting, I should zero out the y-axis. However, such as in the case of the first bar graph illustrated, some would certainly have motive to skew the perception of the information. This assignment has completely opened my eyes to this dilemma. I will personally analyze all important information given to me in the future. It is important to question the data given to you for accuracy always, which is something I'm actually learning at work a lot too, because I do work with a lot of scientists. And so I will be talking to them about some statistic I read online or something, and they completely question it every time. And they ask me more and more questions about it, and they put me on the spot, and they're really showing me the importance of doing something like that. Okay, so for section 3, this one I found to be kind of challenging, and I'm not gonna lie, I had to rewatch that video twice, because some of the information, well, okay, so the big thing was my trying to understand this part of it with the VIN sections. It took me a while to figure out what we were doing here, what these equations actually meant. So I got it now. I figured it out. So we were looking at the number of Americans total, which I'm not sure when this survey was done, but at the time there were 326,000 or 326 million, I'm sorry, 213,213 Americans. It said that 93,300,000 Americans are obese. 10.5% are diagnosed with type 2 diabetes. 32.7% of Americans have high blood pressure. 90% have type 2 diabetes and obesity. 90% have type 2 diabetes and high blood pressure. 86% have obesity and high blood pressure, and 81% have all three. So that was interesting, getting to put this together and figure out, the 326, what the percentage is, that is 100, and then what percentage that is. So again, I'm trying to show my calculations here. I did do all of these. I think that this little error message I'm getting is just because I changed the formula. If I had made this video right after I did it, I could tell you exactly what it is, because I knew what was going on when it happened, but it's not matching the pattern of the formula above. And I think it's because this formula is different than this formula, or this one doesn't have a formula, this one does. I'm not sure exactly, but it's not liking my pattern here. But this is correct information, I think. So we figured up the number that need to be in these VIN sections and the percentage in each VIN section. Then we made 2 different VIN diagrams. So I did watch some of the other videos just to kind of, get a feel for how everybody else was making these videos, and everybody else is making some really pretty charts that I plan on. You said we're going to keep doing these Excel videos. So I plan on learning how they did that because some of them just look so pretty. But mine's simple. So the number of Americans in millions, this 206.1 million are those without any of these ailments, I guess you could call it. So there's 10 million suffering from only obesity, 3.1 million. We already kind of went through this with both. So I illustrated that here. And then over here, the probability of Americans to have any of these is 63.2%. And then that's broken down into these different sections, which we calculated in the chart above up here. So I'm just going to jump right to my report, which is kind of lengthy, but I'm going to read it to you. If I can get over there. Why isn't it staying over there? Come on. Oh my gosh. There it goes. Okay. So according to my data sample, there are 326,213,213 Americans. See, I can't say it. Of those Americans, 206 million, or 63.2%, do not suffer from type 2 diabetes, high blood pressure, or obesity. Those suffering from only obesity total 10 million, or 3.1%. Those suffering from only type 2 diabetes total 0.3 million, or 0.1%. Those suffering from only high blood pressure total 23.3 million, or 7.2%. Americans who suffer from type 2 diabetes and obesity, as well as those suffering from type 2 diabetes and high blood pressure, total 3.1 million, or 0.9% respectively. Americans suffering from both obesity and high blood pressure averaged 52.5 million, or 16.1%, and Americans who suffer from all three total 27.7 million, or 8.5% of the population. I'm going to zoom this in a little bit because I really am a glasses person, but the last time I made my video, my glasses made me look a little possessed. So, oh, that's much better. Okay. It's actually not that much better. There we go. Now it is. So by gathering and sorting statistics or data, we can easily create a visual to illustrate that data. In the case of Americans suffering from type 2 diabetes, high blood pressure, and or obesity, we were able to gather these statistics and sort them into a small table. We can then determine percentage or real numbers based on our data. Then we can condense that information by determining the numbers per Venn section using subtraction. The probability of becoming obese and not suffering from type 2 diabetes or high blood pressure is 3.1%, while there is an 8.5% probability of suffering from type 2 diabetes, high blood pressure, and obesity. If this sample of data were taken in just one state rather than the whole nation, the numbers would, of course, change dramatically. For example, you are more likely to develop one of these problems if you reside in Arkansas or Louisiana, as the probability rate in those states is over 35%. In contrast, you are not as likely to develop one of these problems if you reside in a northwestern state, such as Washington or Oregon, as the probability rate in those states drops to 25 to 29.9%. You are even less likely to develop one of these if you reside in Hawaii or Colorado, where there are the lowest probability rates in the nation at 20 to 24.9%. Okay. So I paused this because my meeting control says turning orange, and I really don't know why. So I could not figure it out, so here I am. Okay, so for section 4, it's showing us these surveys taken of height of Army recruits versus the height of random group of shoppers. This one, I actually ended up calling one of the scientists that I work with to help explain to me coefficient of variation because I did not understand it. I think I understand it now. I hope my understanding of it is the accurate understanding of it. If not, I would love it if somebody would explain it to me better. But I think I've got it. So what we did was we got this little sample of the height of Army recruits, and from there we determined the range by subtracting the tallest from the shortest, the median, mean, the standard deviation, and then the coefficient of variation by dividing the standard deviation and the mean. And then we created this little scatter chart here showing the height of the Army recruits. The data points on here are pretty tightly packed together close to this trend line. From my understanding, what this is saying is that the standard deviation, on average, the average or the medium height, the median is 72. And on average, the Army recruits are going to be 4 inches shorter or taller from that height. And then the coefficient of variation, my understanding of this is that there is a 5.6% chance that if you're coming through this sample, you are going to be in that average, that standard of deviation section there. I don't know if I'm even explaining my understanding of it very well, but that's what I think that means. Okay, so the height of the random group is definitely much greater. One personal, I guess, issue or concern I had with this data group is that I'm not sure what the purpose of these are. Depending on what that is, this does not seem like a fair sample of data, only because we're looking at a height sample of adults, everybody over 18 and older, versus a random group of people. And a random group of people at 34 and 44 inches, I mean, if there's little people at this mall, I guess, sure, that's a good representation of population. But we're taking into account children here, most likely. And to me, you're comparing a group of people that are all 18 and older and primarily male against just the population, just humans. But I'm not sure what the purpose of the survey is, and that's really not my purpose in this, so I digress. So on here, what we did was we gathered this. This is a huge difference, as I said, from 34 inches up to 77 inches. Almost as tall as our tallest Army recruit, only short by 3 inches. On here, we're showing that the scatter plot is just everywhere. Our trend line does look different. The range is 43, so there are 43-inch difference between the tallest and the shortest. Oh, the median height is 60 inches, and the mean, the average height is 58.9 inches. And then our standard deviation, I'm just going to use my keyboard because clicking is not working for me. The standard deviation is 14 inches, and then the coefficient of variation is 0.239, yada, yada. So 0.24 or 24%. So is this saying that 24% probability that in this mall you will fall within 14 inches of the mean height? So 14 inches, give or take, of 58.9, there is a 23% probability that that's where you're going to fall, I think. So down here we did a box and whisker plot. It's illustrating the same basic thing, that there is a very tight grouping of people here. The height of the Army recruits does not vary very much And then the height of the random shoppers is a huge variation. And that's just showing that here from the tallest to the shortest, and then the coefficient of variation in between. Okay, so my report states that in the sample of the height of the Army recruits, the scatter chart illustrates that the results are all in very close proximity to the trend line, indicating that there isn't much variation between the height of the soldiers. In contrast, the scatter plot of the shoppers indicates that there is a much larger variation between the height of the samples. The coefficient of variation tells us that in the statistics of Army recruits, they have a probability of 0.056 or 5.6% of being within the deviation of 4 from the median. The standard deviation shows us that the mean, 72 in Army recruits, 60 in shoppers, there is an average deviation of 4 and 14 respectively. This tells us that there is much more variation in the height of a general population of people than that of Army recruits. The box and whisker plots further illustrate this fact. There is a much tighter box for the Army recruits than for that of the shoppers, showing that the shoppers have a wider variety of height than the recruits. So, moving on to section 5, we looked at sleep patterns of 217 Duke scholars. These scholars, on average, got 6.7 hours of sleep with a standard deviation of 2.03. This one was much easier for me to understand. I get this. So the mean is 6.7, and we're showing that here in our graph. That's the highest point of our line graph here is the average number of people, so the highest grouping of people as well. And then within this 68.2% of people, not people, Duke scholars, are getting between here 4.67 and 8.73 hours of sleep. By doing these little equations here, we were able to kind of determine these numbers. So it's showing that over here in this second quadrant, that, I don't know if quadrant's the right word, but you know what I mean. 13.6% are getting 10.76% of sleep, and then 2.1% are receiving over 12 hours of sleep, which must be nice. I put myself here at a little over 5 hours of sleep. That's probably my average. It's not ideal, but it is what it is. So I am within this, the lower part at least, of this major group of people. I fit within this probability of Duke scholars' sleep patterns. So we also looked at this chart here, which is skewed. And the reason it's skewed is because even though it looks like the highest population of, let me zoom this in so we can see it. Even though the highest population of earners seem to be receiving less than $20,000 a year, it's showing our median at actually $50,000. And that's because, you know, all of a sudden we go from a very small population that are getting, you know, between 180 and 200,000. It just keeps declining, really. And you get to right under 200,000. There's a very small population of people getting that much money. But then suddenly it jumps up, and over 200,000 K, there's a much larger population of people getting 200,000 and more per year. So Because of that, it's throwing off our median. So instead of the median being right in the middle where it should be, it's over here at 50,000, even though that's not the average. I mean, I guess it is the average really, but it's not the number that correlates with our the highest percentage of earners, which is what we're wanting. So according to the samples taken, Duke students on average get 6.7 hours of sleep with a standard deviation of 2.03. This means that on average, the majority of Duke students get between 4.67 and 8.73 hours of sleep. With the bell chart, from there, you can analyze the percentage of students who get more or less than average, which in this case is 4.2%. According to this, as a Duke student, it is 68.2% probable that you receive between 4.67 and 8.73 hours of sleep per night, or an average of 6.7 hours, as previously stated. I approximate that I receive about 5 hours of sleep per night, meaning that I fall in the lower end of the percentile range of the majority of Duke students. According to the 2013 study recorded by Dave Schuler, the median household income is $49,445. However, there is a higher percentage of American families earning less than $20,000, and there is a considerable jump in percentage between less than $200,000 and more than $200,000. Because of these outliers, the graph has been skewed. This means that we cannot illustrate or even properly calculate a standard measure of differences because the median income does not represent the highest percentage of earners due to the higher percentage of earners who are making more than 200,000. So as I said, they skewed it. Okay, so on to the last one. Get a little bit of water here. So Elon Musk selling flamethrowers, which is just a really punk rock investment, honestly. So this was kind of interesting, kind of seeing. So, I've always heard in movies and stuff them saying, talking about losing money or waiting until they break even, and, these type of stuff never really made a lot of sense to me because I guess I didn't really put a lot of thought into it. But, people saying, oh, well, we'd have to sell 2,000 units to even break even. And that never made sense to me because I'm like, but you're selling them at such a high cost, but I get it now. So for the initial investment for his flamethrowing company was $12,000. We know that because once we plugged our formula in and put it to zero, it was $12,000. So the company continued to lose money, and it just kept on losing money up until we get here to this 100. And that's at the lowest point. That's when they had lost the most money at this point of 100,000. Not receiving their profit was not outweighing their investment. But then the company began to finally break even at 203 sales. So started getting a little better. And then at 200, it's still at a loss. And then at 203, as we figured out down here where we broke it down, at 203, we finally saw a profit of $390 whopping dollars. But from there, it really pays off. It goes up to 24,000, 57,000, and then 95,931.20 once he sold 260 units. This is a good illustration of the initial hit that a new company takes. This shows that someone wanting to start a business needs to be prepared to not see a return of investment until well into the startup of their company. I don't know how long it takes somebody to sell 260 flamethrowers, but I don't know that there is a huge market for flamethrowers, even with the military. I don't even know how he managed to sell that many flamethrowers, but he did. So here we illustrated all of this data into this line graph, showing here where he was his initial investment, and then where he just continued to lose money, lose money, lose money. And then here's his lowest point here. This is when he was 69 grand in the hole. And then he started getting better. And then it finally started paying off until we got to our 95. So as much work as this week has been, I actually really enjoyed doing this. I thought it was a lot of fun, and I feel like I really learned a lot. And I am definitely looking forward to see what we're doing next week, which I'm probably going to start right now.